some transformation into JavaScript so that you can see, in a sort of more modern context, how it actually functions, and finish up with that classic old debate of, was Ada really the very first programmer? So to start off, we begin, as all talks begin, with the who am I slide. What is it that I've done that allows me to be here presenting out that way? Or as the slide should probably be called, the ego slide, where the speaker gets to brag about themselves for 10 minutes. I'm not going to bother with that. These are the things that I've done. I'm a developer, basically. I've been a developer all my career. It's what I do. It doesn't matter what it is I'm building or what language. I've always been building something for someone. What is important is what's not on this slide. I'm not working for a university as a computer historian. I don't study as a digital archaeologist. I don't work for British Library. I don't do any of these sort of things. Everything that you'll see here, I have learned by looking and doing and thinking and experimenting, which is a very long-winded way of saying, if I can do it, anyone can do it. So with that in mind, what was the very first program? So it's that. This was in a book called Sketch of the Analytical Engine. It was written by Luigi Menabrea. Now, as the name might suggest, this was an Italian guy, and he wrote this book that describes Charles Babbage's analytical engine in Italian. This was then translated for the English market, and notes were added by Ada Lovelace, formerly Augusta Ada King, Countess of Lovelace, but we just call her Ada. This was note G in that book. So you'd have the book, its original translation, you'd have a series of notes that would describe things in the books, and then this was the appendix to note G, which says, oh, and here is a program that could run on the engine. So it's not even the focus of the book. This is a note of an appendix of a translation of a book. So it's not surprising it's, a little bit small, but we'll break this down and we'll have a look at how it works. First thing is what it actually does. Well, what it does is it calculates Bernoulli numbers, and these are Bernoulli numbers. They're used in various mathematical things. Statistics uses these, engineering uses these. That for me isn't particularly important. If you look at the numbers, you'll see that it goes 0, 1, 2, but 3 is missing, 5 is missing, 7 is missing. This is because all of these numbers, the Bernoulli number is 0. So sometimes you'll see people say the first Bernoulli number, the second Bernoulli number, the third Bernoulli number, and the third Bernoulli number will be -1/30. That's simply because, well, if every other number is a 0, it's not very interesting to talk about that. So the terminology varies depending on who you speak to. So I'm going to hopefully stick to one definition when I need to. But as you can see, these numbers are seemingly random. Positive, negatives, some improper fractions, some not. So there's no real obvious pattern to the numbers that would make it something easy to compute. There's obviously a process behind them. Let's have a look at the decimal version of the numbers, just in case there's a pattern there that we can use to make the computation easier. No, nothing there. So we are going to have to compute these the hard way. So what is the hard way? Well, it's a whole load of fraction stuff, and these are the fractions. Now, at first blush, it looks like a whole load of squiggles. If you hated mathematics, you will probably be in shock by these. But if you look at it, there's not really much going on. Every part of that equation is just the part you had before. So if you look at the number next to B1, it says 2n/2. If you go to the next term and it has B3, you've got that 2n/2, and then those are multiplied by 2n-1, 2n-2. If you go to the next part, it's 2n, 2n-1, 2n-2, which is what we had with B3, and then it just multiplies up with 2n-3, 2n-4. So in essence, you're just saying, do everything that you did before, and then this little bit on top. Now, already, the programmers are going to be looking at this and going, Well, yeah, this is a very easy, obvious program. There's an obvious loop here, there's an obvious piece of mathematics, and there's an obvious result. None of that is difficult. You could look at this and you could code this up in JavaScript in about 5.5 minutes flat. But if we simplify it, you'll see just how easy you can code this. We've replaced all those long equations with A0 and A1 and so forth. And I've shown on the right how these break down and get expanded. But there is one important thing here which makes it slightly annoying. The result is always 0, which means you can't just say, take the last term and add something to it. You've got to recompute everything. Because for the first Bernoulli number, where n is 1, you will do the equation on the first line, A0. When you get to the next Bernoulli number, you'll be doing 2 lots of calculations, and so on and so forth. So you've got to redo every calculation every single time. Now you see where the loops are coming in, and you can see how the the 5th Bernoulli number here is equal to a calculation plus the first Bernoulli number with a calculation plus the 3rd Bernoulli number with a calculation, and so on. This continues all the way up. This is the definition of how Bernoulli numbers work. You need to compute the 7th Bernoulli number, you need the 5th and the 3rd and the 1st. And you need to take those numbers and multiply them by newly computed numbers. So as well as storing the previous 3 values, you've also got to compute something else. Now, we don't need to go into more detail than that. And to be fair, that is probably more detail than anyone really needs to know. But that set of calculations shows you that there is a reason for a machine wanting to do this. If humans were doing it, they'd be bored senseless. So it makes sense that the first program did something that made sense for a computer to do. How? Well, I think it's self-explanatory. Thank you for coming to my TED Talk. Good night. So maybe not. Let's break this down a little bit. So let's look at each line. I've taken a section from the bottom here. Why not? So every single column on that first program is exactly the same. It follows this same pattern. It starts with a number of operation. There are 23 instructions in this program, numbered from 1 to 23. If anyone is old enough to remember programming in BASIC, you'll remember having to type line numbers for every single instruction. This is just like that. It's a line number, nothing more. Next, we have the nature of operation. So if you look at the second column, you can see 2 multiplications, an addition, and a subtraction. There's also a division operation, but that's it. There's only 4 instructions in this system. Add, divide, multiply, divide. That's it. Add, subtract. Nothing more. Next, you'll see the variables acted upon. Now, it's probably a little bit too small to see on this screen, but you have V for variable, and then I think it says V9 times V31. So variable 9 times variable 31. And in the next column, the variables receiving the results. So it's essentially you're saying V31 equals V31 times V9. All very simple, all very obvious programming expressions. Couple of things to note here. As well as the subscript, which indicates the variable number, V9 times V31, you'll see a superscript before it. This indicates the number of times that variable has changed its value. So here, although it's a bit too small to see, I grant you, it actually says 3 V9, which means V9 at this point in the program has been changed 3 times. And then when the result is written back to V31, on this side, you'll see it goes from 4V31, saying variable 31 has been changed 4 times, and when the result is written into V31 again, it becomes 5. This is a very simple way of keeping track how often your variable should have changed, and is essentially an automatic way of debugging your program before it's run, because you're tracking every operation that's been acted upon. In the next column, you can see a statement of the results, what it's actually doing, and then at the end, the equations that you probably saw earlier. The other thing to note here is it says variables receiving the results. Although it doesn't demonstrate it in this example, you can write the results into more than one variable at a time. Now, that's not overly interesting in itself. We're able to do that in modern programming languages. But here, it was dealing with a physical machine. And you had a lot of cogs that would be turning with numbers on them. So the idea of you copying a variable from one place to another isn't possible. We've already said there are only 4 operations. Assignment was not one of them. So you would write a variable into more than one place at a time, which would be the equivalent of doing an assign. Because let's face it, if you're rotating lots of cogs to move things into position, you only want to do it once. So we'll do it when we assign a result as the consequence of an expression. So if there's no assign operation, how do we do the initialization? Because at some point you want to start off your program by saying, let v equal 1, for example. And where on that program is the initialization? Well, it's right there in tiny letters at the top. If we zoom in, you can see it says 1, 2, and then which binary number are we calculating? So v1 is set up by the operator to be assigned to 1. v2, second variable, is assigned by the operator to be 2. This is not a coincidence. One of the methods that it's been used in this program is to say, well, we need a constant for 1. There is no way of specifying a constant. When we looked at the program, every operation was add this variable to this variable, put the result in that variable. There was no assignments. There was no other way. So to create a constant, you initialize a variable, and then you just keep it there. It's also one of the reasons it can take a little sort of getting used to. It's not usual to be programming without assignment. And the third variable in this case, we want to compute the 4th binary number. So in this example, n is 4. So let us look at the first few lines of that program and just take it step by step to have a look. So this is a little bit larger, so hopefully this is a little more legible. So we start off v2 times v3 and put the result in v4 and v5 and v6. And if we look to the column towards the right, that says 2n. Yep, fine. It multiplies our constant in variable 2 by the number of the binary number, v3, and sticking the result into 3 different variables. You'll notice there's a superscript of 1 in each case. This is the first time we've written a value to those variables. Next up, we subtract 1. Okay, we take the 2n that we've just computed, which is v4, and we subtract 1, the constant 1 in variable 1. Next, 2n plus 1. And you see how this works. It's very, very simple. It's just addition, subtraction. Next up, we have a division, which is quite if you're doing a computer, something that calculates numbers, having a division operation is obvious. Of course, we're going to have that. What isn't quite so obvious is the fact that we had division in those days. It would seem that every computer would have a division operation. Yet the computers that we started off with, well, I started off with in my career, which were things like Z80s and 8080 processors from the late 70s, these processors did not have a division operation. If you wanted division, you had to do it yourself. Here, the division started off in the machine. So line 4, for example, 2n minus 1 divided by 2n plus 1. So you take the value v4, you divide it by, wait, hang on. 2n minus 1, we wrote into variable 4, up the top on the second line. 2n plus 1, which we computed on the third line, is in variable 5. And we read left to right. So why is it variable 5, 2n minus plus 1, divided by 2n minus 1, when the right-hand side is saying, hang on, wait a minute, let's have a, there we go, that's a lot clearer. So v4 is 2n minus 1, yet the divide in line 4 says v5 divided by v4. They're the wrong way around. So this isn't the very first computer program. This is the very first computer bug. We've only got 4 lines in, and already there's a problem. Now, I'm not sure what is wrong. The rest of the program actually works. So all it looks like is actually, it's a transcription error. So the printer, given all of this gobbledygook, just had a look at it and put the wrong number in the printing machine. Because once you swap over 4 and 5 and you follow the rest of the computation through, it works, it gives you the right result. So it is more likely to be a transcription bug on someone that copied and pasted it rather than a bug in the program itself, which is kind of good news. But needless to say, there is a bug in the program. So let's try and put this into JavaScript. Now, when I created this, I created a very basic simulator. I do like emulations. I write emulators in JavaScript a lot. I've written emulators for Space Invaders and Spectrums and things like that. So writing simulators isn't really a big deal. It's not as clever as people like me want to make out. So I'm just going to create a big array. Each object in that array is going to give us the operation, the source variables, and the destination variables. As we've said, you can write the result into more than one variable, so that has to be an array, I'm afraid. A little bit ugly, and it's only necessary for one instruction, but let's code it anyway. We then set up our little program counter. We start at line 1 and we work through. Big switch statement saying, what operation are we doing? Perform the calculation, multiplies, adds, subtractions, and divides. Store the result into the mill, which is like an accumulator. In the original text, they call an accumulator a mill, so I've decided to name my variables accordingly. And that mill result then gets written back to every single variable. And that's it. Increment the program counter, back you go. Very, very simple, works a treat. So now we've got a simulator. Let's just take a step back to this. You remember that? In order to compute the 5th Bernoulli number, we need the results from the 1st Bernoulli number and the 3rd, and we do some more calculations. So we need to go back and do things again. So we need a loop, and there it is. The very first loop, wedged between lines 23 and 24. And what that text says is, here follows a repetition of operations 13 to 23. The very first loop. The first time we actually had any form of algorithm. We had control flow, we had program flow, we had a way of doing things. But there's a problem. Every single line of those instructions indicates which variable we're using. V10 minus V1, V12 plus V15. Every single variable it mentions is a constant. Why is that important? Well, if every single variable is a constant, how do you get the previous Bernoulli number? You've calculated this Bernoulli number and put the result in V10. Where are the previous Bernoulli numbers? Well, they were also written into V10. So there is no way of saying, well, next time round, I need to write the results into V11 or V12 in order to maintain the past results, which means the program also would never have worked. You've quite literally got the very first case of Stack Overflow, where you'd have to do a copy and paste of lines 13 to 23, copy and paste them, change all the variables until they match the next Bernoulli number, and repeat it. So in a sense, this isn't a loop. We've been cheated. The very first program has a bug in it, and the very first loop won't work. So in order for the simulator to work, for me to see this program, you need to make a couple of small changes, which is to introduce this concept of, I wish to write it into a particular array element. So let's continue back on the transformation process. If you want to look at this, the GitHub link should still be up as far as I know. So you get to see each of the stages that I took. So it starts off with the operation as the simulator. By looking at the program, I got to understand how it was working. Variable 2, for example, we know always contains the constant 2, so I could replace that. The variable 1 always had the constant of 1, so I could replace that directly. 2n minus 1 is another variable which I understood, so I called that n2m1. n times 2 minus 1, because you can't start a variable with 2, obviously, that would be silly. And I did this for every line of the program, breaking it down until I ended up with a program that looks roughly like a genuine piece of JavaScript. Called things numerator. I'm too lazy to write denominator in full, but you can see that this program would make sense and this would be understandable. You could give this to someone and they go, yep, I see how that computes binary numbers. You'll also notice the index to result variable that I had to create there, just so that the 3rd, 4th, 5th, 6th binary numbers were stored somewhere that we could use for calculation later. So there we've got our program. We've verified it existed, that it worked after a few tweaks, and that we can transform it into something that's legible. And that's the very first program. And this is where it gets fun. Now we get to the part of, well, was Ada really the first programmer? Because it's very easy to say no. As we've established, there's a bug. We get 4 lines in and there's a bug in the code. Now, granted, it's not Ada's bug, but there's still a problem. And when I was working through this, it took a while for me to realize that these things were around the wrong way. It's not a good start. The notation is a bit iffy. We've all had programming languages and things where you've seen that notation and you're thinking, this is not the right way. But it works, it describes the problem, it covers the algorithm. The loop we've seen doesn't work. There is no way that would have ever worked. There was even no hint that it should have worked. It didn't even, there's no note to the note that said, oh, by the way, I know we've got to change all the variables because we've hard-coded the results. No, but it was obvious that it had to have a loop, which was a novel concept. Other people have claimed that she's not the first programmer because she's translating someone else's work. Well, it's a translation, yes, maybe, but there is still innovation in the programs. And obviously Babbage had already written programs. He designed the machine, so obviously to make sure the machine works, he would have built a program. Unfortunately, he didn't build the machine because he never got round to building the analytical engine due to lack of funds, but that's a history lesson for another day. So if Babbage had already written programs for his own machine, then surely he's the first programmer. So why are we trying to claim that Ada is? Well, Babbage's programs were a little more than hello world. Because let's face it, why would you do any more? You've proven it works. That's the hard part. That's the fun part. Move on to something more interesting. So why was she the first programmer? And there were lots of arguments about why she shouldn't be. And it often comes down to, well, what is a computer? Because if you want to be the first computer program, then if you change the definition of what is a computer, then the definition of the first computer programmer naturally also changes. I mean, up until as late as the 60s, the word computer was still used for a human being that would do mathematics, usually with a pencil, usually on paper. So the word computer is a comparatively modern term. Ada would never have used the term computer programmer. So can we really ascribe her that title when it would never have been used? The same is true of programmer. So with all these possibilities of saying she can't be the first programmer because of this, because of that, I looked at it a different way. I said, well, instead of finding all the reasons why she's not the first programmer, let's find out why she should be the first. And all I need is just one argument. If I can find one argument for myself of why she should be, rather than why she shouldn't be, I'm happy. And the argument I came up with was this. If all this work had been done by a man, would he have been considered the first programmer? Bear in mind the age of which Ada grew up in. It's a not unreasonable question. And thinking about it, if Ada's work had been done by a man, he would have been considered the first programmer. So I think, yes. Therefore, Ada was the first programmer. And therefore, this was the first program. So what have we come up with? Well, the first program did decimal approximations of Bernoulli numbers. Nowhere does it say what a Bernoulli number is. The book just describes the process of Bernoulli numbers. So it was obvious that everyone who was able to read that book at the time understood Bernoulli numbers and didn't need an explanation. We've seen the algorithm, what it does, how it works. We've seen that Ada was the first program. And it wasn't just this program that she wrote. There were other programs in the notes, in the appendices of the book by Menabre. There were other comments that she wrote. She discussed how the numbers in programs don't necessarily need to represent numbers. The numbers of a program could represent letters or words or musical notes. So a computer, as well as just munging numbers to produce numbers, could munge numbers to produce poetry or music, which is what MIDI is. MIDI is musical information data, so note 60 on and a C gets played. So essentially she'd come up with the ideas that would later lead to Photoshop and to MIDI musical instruments and all sorts of computer loveliness. So I heard a ding. I'm assuming that means time is beginning to run out, so I shall leave it there for questions. And Alt-Tab back to the app. So
it was really interesting. How long did it take you to actually put that together, like to analyze the program and
so lots of things were done separately. So I spent 10 or 15 minutes in a lunch break, every lunch break for a week, doing sort of the transformation, understanding the program. So ultimately there was probably only a couple of hours of actual thinking and understanding and pulling it apart. But it was stretched, because it was stretched over a week, it wasn't focused in those 15 minutes of time. It was like I'd do the 15 minutes and then on the train I'd be thinking, yeah, I wonder what they mean by that idea and why are they doing it this way? And then using those sort of idle minutes, as it were, to then flesh out the knowledge of purely here is an addition. Because when you break all computer software down, it's just here is a number, we do some maths to that number to get another number.
Mm-hmm.
Everything ultimately boils down to something so fundamentally simple, but it's how it does it. With video streaming, all that's doing is sending one number over here. If I want to lighten it, I'm just modifying that number slightly. But by doing it to enough numbers quickly enough, it does fantastic image manipulation.
Yeah.
So there was a level of understanding beyond the just, well, it's modifying numbers. Okay. And that comes gradually over time. It's the difference between learning about something and then truly appreciating it. I can learn to play a piece of music.
Was the bug really serious?
It was really frustrating. It wasn't serious because you're stepping through in the simulator that you've written, and you're going, this is doing the divide like it should do. That number is coming out of there. It's being divided by that number. It's going there. I computed the first 5 or 6 Bernoulli numbers by hand using the algorithm, and as a proper dry run, like you're supposed to in proper computer science. And I was, I'd got pages of notes of me doing these calculations, and I'm looking in the debugger and I'm looking on the page. It's like, these numbers match. The simulator is working. Therefore, therefore the bug must be in the program. And then it's a case of going through. And when you start going through it and you properly read it rather than just copy and paste it from that JPEG of the program to your code editor, you suddenly go, yeah.
For her time, was that a serious bug? Like, do you think like a lot of people lost a lot of money, or because they wouldn't know, right? We don't have the...
They wouldn't know, yeah. As far as I know, there is no web URL in that book that indicates, for errata, go to this website.
Yes.
And you've got to bear in mind, at this time, the number of people, although it's comparatively late 1800s, it's still a case of, well, not that many people would read.
Yes.
The person in the street would not be an avid reader.
Yes.
They certainly wouldn't be an avid reader of computer literature. But it wasn't in there. They wouldn't have been avid readers of literature that had been translated into Italian into English, or the appendices of that, or the notes of the appendices. So essentially, you've got one line in an image in an appendix of a note of a translation of a book. The number of people that got that far were probably already smart enough to spot the bug before I did. They're obviously that smart, and and as I said at the very end, there's no description of what Bernoulli numbers are, how they're used. So it's obvious that the reader is expected to understand Bernoulli numbers, at which point you can tell the level the book is pitched at. So they probably didn't have too much issue with a bug, particularly as the machine never got built.
There was no Stack Overflow as well.
Yes, that's true. Yes, maybe I should set up a subdomain on Stack Overflow for the Analytical. It'll just have one question.
Yes.
Why does this line not work?
That's great. I'm going to close the session and we're going to go back to the tables. And if anyone wants to ask any questions to Stephen, they can come to table 1 and Stephen can ask any questions before we close off completely. Thank you, Stephen. It was really exciting. I learned quite a lot during my lunchtime, and thank you very much.
Thank you. Bye for now.